Yeah, welcome to the Fluids and MHD seminar. Today we've got Geoff Vasil. As your laptop crashed again.
Well, that thing made it do it, yeah.
Okay, so
I don't know. Yep. Please up.
From University of Edinburgh. Did his PhD with Keith Julian and Nick Brummel in Boulder, and their postdoc positions in CETA in Toronto, in Berkeley, and spent a decade in Sydney, and moved to Edinburgh last year, where he's now in the School of Maths as a reader. And we're talking about, not me, the magnetorotational instability in the solar convection zone.
All right, we're going to get back on this. Okay, thank you very much. Yeah, sorry about that. So yeah, it's a pleasure to be here. I've been in Edinburgh for 6 months and I'm really enjoying it, and especially being able to come down and see folks like yourselves. I'm going to talk today about some solar physics, which is what I did quite a long time ago for my PhD, and have kept an interest in ever since. But some of you know about data listings, so this is something that I'm happy to talk about and answer questions about at some point. And there will be some data listings in this talk, but for the most part, this is going back to my roots. And to some degree, it took 15 years between the time I thought of what I'm going to be talking about today and actually be able to get somewhere on the problem, because it actually needed almost everything that's in data list today. So now that we have this this tool, we're having a lot of fun employing it downrange on some interesting problems, and the solar physics problems are in my favor. So this is something I just like to talk about. I like to have some fun. This is, does anyone know what this is? Somebody must know what this is. I would be stunned if nobody in this room has been there. It's Newgrange. It's in Ireland, and it is a passage tomb. It's quite big. You can see that those are like decent sized staircases. The person is like that. It's 50 meters or so, and it is my humble opinion probably the oldest solar observatory in the world. Okay, so it's lined with the sun, and it's like probably designed to shine down the sun. The sun shines straight down the passage, and there were people living. These are older than the pyramids, 5,000 years. This is, and so people have been obsessing about the sun for quite a long time, as we should. And this wasn't obviously for science, probably, maybe not, maybe it was. But I could imagine they were able to actually see something on the surface of the sun at the time if they were looking carefully. And the first like actual science done in a systematic way was 400 years ago now, nearly, a bit more, by Galileo, right? And he pointed at this, a telescope like this, and certainly it was only about that big if you've ever seen one replica of something in a museum. It had, it's a very small diameter, but nevertheless he was able to shine images on a sheet and make drawings of what he saw were sunspots. And actually, I think I originally got an older version of this movie from Steve many years ago. Do you have a newer version of it? You can get a newer one, by the way. So I had a grainy version that I had from you for forever. Rice University has all these images on their website now. So I made a new version of it. But the cool thing is you can animate these things, and I just love. I never get tired of watching this, right? So I don't know. Many of you around here have probably heard something about sunspots, I would expect. But there's these black dots, and they come and go, and they move around. And Galileo was able to see that the sun indeed rotated. What I also love about it is that we know now that that's actually what sunspots really look like, right? He wasn't able to cheat in some way, right? It's kind of gets boring to see things like this, and now you know that, like, but he was literally doing this for the first time, and you can see this multiple structure. You see dark spots surrounded by networks of kind of complicated structure, and he just was drawing what he saw. There was no baggage that came with it. Of course, nowadays we use much more sophisticated things. So this is the Solar Dynamics Observatory telescope in orbit now and making images of some I'll show today. You see ground-based stuff. That's the Swedish telescope, which is in the Canary Islands, and I have some things from that as well. And then other satellites, there's a Node satellite. And so we have way more sophisticated tools. But why I'm talking about these historical things is that I think it's perhaps a little bit bold, but not that wrong to say that this is the oldest unsolved problem in theoretical physics, is my view, right? So this is a question that in some sense was asked at the dawn of the scientific age 400 years ago, and we really actually don't know why that's happening. We know what it is. We've learned a lot. We know it's no magnetism and such, but we don't really know what's causing it. And I suppose I probably will never solve that question, because why would you be the one to do it? But the point is that I think there are things that can still be pushed forward with modern tools. So what are we trying to do more in detail? A sunspot now. This is something that the Canary Islands could have seen. That's about to scale. And interestingly enough, I picked this photo because that up there is the International Space Station, Space Shuttle. But if you do it and you zoom in, again, this is like what Galileo would have loved to see. You see this network of connected regions. Connected regions of magnetism sitting in a sea of really raging convection, turbulent convection, certainly the most turbulent, strongest convection in the entire sun. I'm very surprised otherwise. And again, we don't really know where it comes from. We know what it is. But if you take a bunch of magnets and you put them all the same polarity and you put them in a tray, magnets of the same polarity repel each other from the sides, right? So if I put them in a tray and put a lid on it, for example, and shake them up, they'll all end up kind of repelling each other and end up some distance away from each other, right? They won't clump together. This is magnetic field, certain polarity pointing out at you that all clump together. So clearly, more than just magnetism have to happen here. It has to be something involving the flows, but otherwise we really don't. And people say things like negative pressure instability and stuff like that, but those are just words, right? Yeah, for scale, that's Europe down there. And then it was only, I remember this video came out when I was in grad school, 2006. And this was the first time somebody really actually saw a sunspot emerge in real time. This is from the Hanode satellite. And I've watched this video many times over many years, and I still have no idea what it's doing, right? You watch it again, and you're like, if you put a bunch of black and white magnets in a tray, the white ones are going to stick to the black ones. And the black ones, it wouldn't do this, basically, right? But somehow it's not there, and then it's there. And you see it separates out and you get opposite polarity spots. And of course, why it's important is occasionally these things erupt. This was a flare in 2012 that missed Earth by 9 days, and had it hit Earth, it would have been similar in size to the Carrington event, which existed in sort of pre-industrial age or at the beginning of the industrial age. But if this flare had hit us, it would have been very bad, trillions of dollars of damage if you hadn't been prepared. So again, some other kind of fun history. And we're now about 100 years, almost exactly 100 years after this. But Walter Maunder was a scientist who did a lot of early quantitative measurements of solar phenomena, and he gave this address to the Royal Astronomical Society, saying the Royal Astronomical Society was founded in 1820. At that date, it was known that there was a sun, but sometimes there were spots upon its surface. The sun rotated on its axis. Practically, that was all. And Steve, I don't know, we can't say much more than that, can we? Yeah, it's in spite of the fact that we know a lot of the what, we really don't know a lot of the why, right? And actually, Maunder really did a lot of fleshing out the what. So I'm going to tell you a bit about that. And I just got to say, I'm sorry if it isn't your style, but I love old papers like this, and you actually go and look at them. I don't speak German, but I know people who do, of course, and you can translate this, and it turns out to be quite readable and modern. But the first details emerges in the 1850s regarding what the sun is actually doing. And I like to make this point. This is, again, contemporary with the founding of the sciences of electricity and magnetism, thermodynamics, before relativity, quantum mechanics, Big Bang cosmology. So, like, all of the major revolutions of science have come and gone and been solved and turned into technology, and we're still here wondering what these damn spots on the sun are. To see that you really, this was a different time. This was a paper written to the Astronomical Society in 1858, and it turns out if somebody died, you could put an apology in your paper for your paper not being very good, and they would still publish it. Okay, I fully hope by the time the society would meet again, different members of tolerant better discussion, but like, sorry, like, so yeah, nobody cares. So Walter Maunder made one of the most, one of the coolest observations, I think, as well in the history of science, which just the commitment. So this is his actual diagram from his paper. And what he did was he went out every day, or maybe every other day, and he looked at the sun, and he made a note of, on that particular time, on this axis, what latitude the features were showing up at, right? And then he just made a note of it and went back, kept doing that. This is 1874, 40 years later, he was doing the same thing. So what a commitment to keeping records. And obviously, if you were to go that far, you'd be like, okay, it's just a bunch of scatter, who cares? And then flip, and then, whoa, and you keep doing this. And after 2 cycles, I'd be pretty excited. And then you keep going. And this paper was published in 1922 because something happened in between those times. But again, if you feel like you have some work that you haven't submitted a paper for, don't feel too bad. So this is what's called the butterfly diagram, and it's this pattern. It's not, perhaps it's not exactly like what you think of a wave, although it might be, but it's a pattern. It's where the spots appear. It's not that the spots are moving. The spots pop up, live for about a month, and go away. But the location where they prefer to be does drift towards the equator and then annihilates and then appears again, right? And again, we don't have any real idea of it. I mean, we could say it's a result of some sort of oscillator or something like that. But those are just ways of rephrasing the same thing. Some more details, and I have a lot to get through, so I'll probably go quicker here. But at some point, somebody actually learned that this is a magnetism. George Hale, pointed a magnetogram at the sun and realized some more patterns, that there were pairs of polarities that were leading and trailing each other. In the 50s and 60s, Babcock realized that the sun is a big magnet, it's a big dipole magnet, and that dipole is flipping itself over. Sunspots have a field strength, if you want to recall, for about 1,000 Gauss is a good number to remember. And the background polar fields have on the outside of the sun are in the order of 1 Gauss. So I'm going to use those numbers later on. I'm going to discuss them in more detail. But more features. And one of the things that I would say, though, in the modern solar physics world that isn't happening as much today, whether or not it's possible is another question. What doesn't seem to happen as often, which I would love to have more of, are new laws. So this is like Hale's law, Joy's law, and Maunder, butterfly diagrams. These are qualitative descriptions of statistical phenomena that are not always true, or maybe even seldom true, but more true than they're false. And that these are facts that you can try to fit your theories to, right? So if you have a theory, a pet theory of the solar dynamo, you want qualitative features to check it against. Okay, you're not going to get the quantitative details right, especially initially. Like your Boost-Nest model isn't going to get the details right, but you might get leading and trailing things, or you might get that. But we can easily do now reproduce most of these qualitative laws, but what we don't have today with modern data science are new laws. So if you look at solar data, it's just like this fire hose of things, spectra and all that, but there's not a qualitative description of a lot of things. So what's an exception to all this stuff? So the error of the law is kind of going away. And then this is what the solar cycle looks like all at once. So the sun is mostly not magnetic, and then it lights itself up at some point, and then there's solar maximums. This is from 96 to 2006. It lasts about 10 years or 11 years. And this is what it looks like altogether. This is the cycle, and this would repeat itself. There's some other beautiful images. This is from Solar Dynamics Observatory, stacking together maybe a couple of years worth or something. I don't know, some long period of time. You see these like nice, big, bright bands. This is certainly a persistent feature that lives for multiple years and some scale. So again, any pet theory of yours, I would say, should should look qualitatively like that. If you can't explain it, then we need to think harder. And then what's more, another qualitative fact, that the cycles tend to themselves wax and wane very long. Maunder minimum, the famous Maunder minimum, which the Galileo observed the first sunspots in early 1600s, and then shortly thereafter it disappeared, and he kind of lost interest. Other people have been keeping records, and they actually, there's evidence that the solar cycle was still running, but at a much lower amplitude, but not producing spots. And again, the reasons for this can be speculated about. I tend to think that there must be some threshold strength of the field to create spots, and spots are kind of like a proxy, and so it can kind of run fine, but you need to have an extra oomph to the spots are like a bonus. And then there's speculations about what impact it's had on climate, but like Edinburgh never looks like this, right? And this is the London frost fairs, and yeah, I guess these are regular enough people to go out and enjoy a hot beverage. So again, some of the more of the what's of the sun. It's got a zones, it's got a convection zone, it's got a radiated zone. So it's being nuclear burning in the center, of course. Radiation's leaking itself out. At about the upper 70% of the sun, you begin to become unstable turbulent convection. I could give another talk about my views that these cells, as drawn by an artist, should not be circular, they should be cigar-shaped. So there are rotational effects that take place. It's a complicated mess, perhaps, but this is a view that the solar cycle, factual what's of the solar cycle are simple enough that I think once we find the answer, we'll go, aha, okay, that seems to be like you're going to be able to tell somebody the story in an hour, right? It's not going to be a book with 1,000 pages, perhaps. I mean, obviously the details will be complicated, but hopefully there's a series of like clock-like mechanisms that one leads to another and tells you what it is. But have to exist in all these things. You have to get it all right.
I might be asking a naive question. We could ask what that dottiness is that's going out with. Is that meant to represent photons?
Those things. Yeah, those are meant to represent photons.
Oh, okay.
Neutrinos. Yeah, perhaps they're neutrinos. I don't know. Yeah.
I've seen them before.
Something else that Maunder observed was that the spots near the equator tended to move a little quicker. They tended to go around a little faster than the spots on the poles, and so he attributed that to a differential rotation shear flow. That is essentially, to some degree, the ultimate driver of magnetism. It has to be, no other way around it. Well, so, and then now with modern techniques, with acoustics, you can, and I for brevity of time, I cut out some of the details here, but heliocosmology is another one of those qualitative things, again, that happened in the 80s, really, that in my view is well deserving of a Nobel Prize. It's an amazing achievement where we know about the structure of the inside of the Earth because earthquakes happen and seismic waves bounce around, and we can infer what the interior is. And that's pretty good, but the sun is much better because it has this roiling convection at the surface, and that generates essentially loudspeakers that make a lot of noise, and the sun is filled with sound, and you can look at the way that those waves move around and do detailed calculations and find that the sun is rotating. It's like a jet. It's going around the equator, and the pole or region is like a cow that's sort of counter-rotating relative to the whole bulk. And then the inside is kind of moving at some constant rate, like a solid body. And in the middle, something. And I want to point out that, like traditional solar theory models, well, the magnetic fields come up about up there. That's where they sort of begin, and then they move down there. And there's a lot of models saying the tachycline, which is region here and here, where the different rotation shifts. But the place where the magnetism shows up is where there is no tachycline. So what's up with that? I don't know. So I could also talk a long time about traditional solar models, which I worked on, and many friends of mine and people in this room have done, and talk about why I think there's real issues with all of them. I think everybody would agree that there has to be issues with all of them. You don't have the answer. But I'm going to really focus instead on this region of the surface. So I'm going to propose a hypothesis that perhaps the reason why things are, you see them at the surface is because they actually start at the surface. And there might be reasons for that. And we're gonna pull on that thread and see where that leads. Okay, so traditional models would say tactical and perhaps even convection zone. Those could still be right, but I'm going to talk about what if everything below the surface is deep below the surface is really doing something very different than the surface, and it all is happening there. So this is a picture that Nick Brummel drew as a sketch that gets passed around. And this is a picture that walks through the whole process as conceived by many people over many years. And I'm going to just sort of do that today. Okay. So this is, I think, the most interesting piece of the puzzle that gets very little attention. This is from a paper in 2002, Vorontsov et al., a science paper. This is helioseismology. So I didn't make this picture by far. And what they do is you march out and you measure the differential rotation at the beginning of the solar cycle, call that t equals 0. And then you do the same thing a year later and you subtract the results. And then you do the same thing 2 years later and you subtract the results. And so this is the time dependencies of the axisymmetric differential rotation as a function of depth and latitude, right? And if you focus on that picture, does anybody want to tell me what it looks like? What might be a mathematical name for that picture? Okay. I think it's a mode, right? I mean, it's got a wavelength, and what's more, and then there's reasons why I know you could get fussy. You could say about measurement things, biases and such and such. So there's lots of caveats here. It wouldn't be good, but it doesn't start down there and go up there. It starts up there and it goes down there, right? Like I think that's at least what this picture is doing. Whether the magnetic fields are doing that, that's another question. But this picture is doing that, right? So it's a mode and it's shallow, and that got up there smoking a cigarette, by the way. You can't see it. So I think this is a big fluke that doesn't get enough attention. So this is also happens to be where the near surface shear layer is. The strongest shear inside of the sun doesn't get a lot of attention, in my view, because it's actually quite thin and you can't see it on pictures very well, whereas the second line really jumps out at you. But this is where the near surface shear layer is, so maybe there's something going on there, but it looks like the action is beginning there. And these patterns called torsional oscillations are well known to follow the magnetism. Okay, so the magnetic fields will begin up here and they'll kind of move down. Who knows what's going on in the pole? Okay, that's really totally crazy. But let's just think about low latitude. And what's more is not only that, it kind of stops actually after it gets, like that's about it. It doesn't even get to the bottom. Okay. So if you look at the mean shear, and rather than look at the regular old rotation rate, we actually look at its derivative. The near surface, and I color it negative in red to make it clear what's going on, and blue is positive. Two things. One is that the shear near the surface in this way is up 400, and the shear near the anticline is sort of in the 200-ish range, so it's twice as strong. And then what's more is that the shear at the surface is like all red. Okay, so it's all negative. So we have two clues now. So we have the torsional oscillations look like a mode that lives near the surface and propagates inward. And we have the differential rotation near there is strongest and negative. And so perhaps those two things relate is the idea. So what could be going on, right? So some of you have already studied and know about where I'm probably going with this, the magnetorotational instability. If you don't, I'll go through it a bit. So suppose you take the situation of a shear flow, right? So you have fluid particles, A and B, and they're flowing around a center, an origin about 60 kilometers away. And if they're moving at slightly different rates. So if you just let them go, they'll begin to drift apart from each other. Okay, so the fluid will begin to shear. It's mostly stable, right? That's kind of why this whole works. The orbital frequency is given as a function of gravity, mass, and so it's what you call Keplerian. And Lord Rayleigh said that if I take a rotating hydrodynamics in 2D polar coordinates, doesn't details here, that it is stable if the local rotation rate is a function of radius squared times radius to the 4. So this is the square of the angular momentum is increasing outward, then it will stable. And if it's negative, it can potentially be unstable. Okay, this is called the Rayleigh criterion. For orbiting objects, you can just calculate it. It's equal to the mass times Newton's constant, positive. So that was a bit of a conundrum because things that are orbiting disks, people know they're unstable, and I'll touch on in a minute. However, if you do something silly and you attach them by a weak spring, if you attach them by a strong spring, that's the same thing as bolting them together, and then they're just going to become one thing. But if you attach them by a weak spring, they kind of maintain their independence, but they're able to transfer angular momentum back and forth to each other. And what they do is they'll drift apart, and as they drift apart further, they transfer more angular momentum apart further. And what happens is that there's a weak spring constant, if you like, that transfers angular momentum from the high region of angular momentum to the region of low angular velocity and so on. It catalyzes this instability, and the more it happens, it keeps going and things fall apart. And this was accidentally done in space. They hung a space cable out the window with the space shuttle a while back and let it go, and it snapped off. And they learned after the fact that it's probably this kind of a mechanism at play. Down on Earth, it seemed like the cable would have been worked out strong enough. Didn't think about this. So the idea is that Chandrasekhar and Velikov and the Soviet Union around the same time, almost within the same year, occurred to them that a magnetic field can catalyze an instability that would be otherwise stable, and that the condition for stability becomes that the angular velocity has to be increasing outward, but if the angular velocity is increasing inward, it can potentially be unstable. And the Keplerian flow satisfies this. It's in the middle ground. And this is what our friend Steve Balbus, who's at Oxford now, occurred to him that he said, I think you could use this to explain why accretion disks accrete. Right? So they should be stable according to Lord Rayleigh, but that's actually almost observation, but they're very bright, and that implies that a lot is going on, but they're magnetic, and then this has led to 30 years of good and interesting science. So that's the magnetorotational instability, but they didn't get a lot of attention in stars. And when I was a PhD student nearly 20 years ago, people in the solar physics community were still asking what this instability even was. Like it was like really hard to actually find out. But it occurred to me, and actually Geoff Vasil, who has a Zoom call, who's here visiting, and we'll be happy to talk about Daedalus questions and around those things. It's happened so we get along really well, because we oftentimes find out that we had the same idea at the same time completed. This happens all the time with us. So I would give him credit. He had the same notion right around the same year or so that I did as well, back when we were both younger. And the idea was, well, so the sun has a dipole field. We know that. It goes trucking through in the right configuration. So Balbus and Hawley, this paper, they put a background field through, put shear flow, and then form these stable blobs. Well, the sun has got differential rotation near the equator. It's negative, correct sign, strong. There's a dipole field near the surface. We know that. It goes in the right way. And there's a stability condition. It says, and here's roughly speaking what it is, right? So the stability condition requires a magnetic field that is weak enough, interestingly enough. Again, if it's too strong, they're just pulled together. It requires enough space. That's a wave number, so you need the wave number to be sufficiently small. It needs a rotation. It needs a differential rotation, and it needs, importantly, a negative differential rotation. So that's all the conditions that are met in shear. So I did some preliminary things over the years here and there, but we really needed Daedalus to make real headway on this problem because of the sphericity and all the complicated physics going on. So this is our usual kind of slide. This is my friends, my team. Daniel Lequinay, Keaton Burns is really the genius, and then Ben Brown, of course, is an office mate of mine in grad school. Geoff Vasil is a contemporary of ours. So, and it's just been a great fun. You know, all of these different pictures are examples of things that people other than us and some of us have done. And many of you I know have used it. We'll be around to chat some more. So I'm not going to go into an introduction to Daedalus, but a very short introduction to Daedalus, I guess, is that if you don't know, right, it's an open source code that you're allowed to type in your equations if you like, and it turned out it was easier to make a code that can solve all partial differential equations than it was to make a code to solve only the partial differential equations we needed. And so you type in these things, and then you push go, and it will make a simulation in a box or a sphere, for example. It's written in Python, using Python. It's open source. You can try it out on your laptop, and then if you like what you see, you can run it on a really big supercomputer. And it's been a lot of fun. And then this is not Daedalus. This is music code, which is a really sophisticated thing. Does some great science. Music, run out of the University of Exeter, Isabella Maraf and her group got a lot of money to build this a few years back. And the point is that they cut the coordinate singularities out on the advertisement. Okay, so there's no center and there's no poles. In polar coordinates is really difficult. If you look at the Laplacian in polar coordinates, you'll see 1 over r squared, 1 over sine theta, all over the place. And if theta is 0 and r is 0, then it's like really tricky to what to do about that. And as far as the actual flows are concerned, they don't care, but the coordinates do. And numerically, computationally, it's very challenging. So we spent a lot of effort, Daedalus, making the spheres work right. So circle harmonics is obviously the solution to that, but also in the center as well. And there's a lot of bells and whistles that just you have to get right. And we've had a great fun doing this, but now that we can do this, we can run like full sphere. So this is a simulation from Evan Anders, who was probably here not that long ago. You know, and actually this looks more singular in the center than it actually is because there's a line that cuts it through. But basically, and the movie's a bit jumpy because it's probably going back before it gets here through Zoom. But yeah, there's no ill behavior going on in the pulse center, and because we're only using mathematical functions that can behave nicely. Okay, yeah, we're doing over time. Okay, so the idea is to kind of get the gist. Take configuration we believe exists near the near surface layer of the solar convection zone. Put in the relevant physics and push go and see what happens. Okay, so we take the full stratified and elastic magnetohydrodynamics equations. We linearize around a background polar magnetic field. I didn't exactly say dipole, but it's two-dimensional axisymmetric. We take a rough enough approximation of the observed solar differential rotation as measured by cosmology. We take a rough approximation of the observed solar density as a function of radius in the outside layer. And plug it into Daedalus. We use realist boundary conditions, and all of these things we perturb them because we don't really believe them exactly, but we try differential rotation and something a little different than that, whatever. But same with boundary conditions. We play around with those potential field boundary conditions, perfectly conducting boundary conditions. We know that there's a dipole and a vacuum on the outside. It turns out, for reasons I'll say in a minute, I think that potential field boundary conditions are actually not the most relevant. It doesn't really make much of a difference. We plug it in, we look for 3D eigenmodes, and then we're going to see what we can do with that. So here are two examples of magnetic field profiles that we use, or some linear combinations of these. This is a dipole and what it looks like. And near the equator, the lines more or less, again, go vertical, as the local Cartesian approximation would indicate. But near the pole, middle, I don't know, it's like hairy and there's radial things, and it gets complicated. But this has no current, right? This is the curl, and this vanishes exactly. And then don't worry about the numbers that they mean, but this is some other simple background polar field profile. And this one is got a bit of dipole in it and some more stuff. This one has a little bit of current in the simplest way, but hey, that's okay. But this one has a nice feature that the radial field vanishes at the surface. And so what you have, it's like Las Vegas, right? Vegas stays there. And initially we were doing that, but then we switched to this at some point because I said that the field strengths of sunspots are 1,000 Gauss, and the field strength of the dipole field outside of the sun are 1 Gauss-ish. But there's been some work, and we actually found this work because we started doing these calculations and kind of led to it. There's some work that suggests that the field strengths inside of the sun are bigger than 1 Gauss. They might be 100 Gauss. And there's a lot of uncertainties about the configuration. It could be 200, who knows? Probably not 1,000, but it's potentially a lot stronger just below the surface. And there's some helioseismic evidence of that, indicating that that perhaps a stronger field, slightly stronger field, is maybe correct. And so then that's another way to say that there's some mechanism keeping it trapped. Okay, Steve, do you know a mechanism that you can keep magnetic field trapped? What's a good one? Magnetic pumping. And what do we know exists? So this is actually ending at 0.99, but what do we know exists at 0.1 to probably about 0.99 is the strongest turbulent compressible convection universe. So there's a hypothesis perhaps that very strong magnetic pumping. So Steve and others have done some excellent work on magnetic pumping, but that is a very compressible effect. And so there's a potential issue that you can actually keep a stronger field suppressed with this very strong pumping and get a slightly stronger field, which actually makes everything work a little bit better. But it's not a disaster either way. So that's a potential bit of story that I guess we stumbled across. So that's the idea, is that you have a pumped field. But then otherwise, it can be. And that also makes some sense. Also, it's a little confusing how you get 1,000 Gauss sunspot out of a 1 Gauss background, but getting a 1,000 Gauss sunspot out of a 100 Gauss background seems to be pretty plausible. And then you can do some playing around. So one of the things you can do is here's the actual differentiation profile you use. It's fit to the near surface shear layer data that I used before. Here's the density that we actually use. And it's almost exactly a polytrope, except for where the action happens. So down here, it's off by about a factor of 2, even though those numbers are small. And what's cool is you can actually do this like simple estimate, nonlinear or linear stability calculation, and you can show that you can actually solve this eigenvalue problem with a magnetic field strength as the eigenvalue, and show that field strength below about 1,000 Gauss, then you should expect some MRI. For above that, the field is too strong to cut it off, but nobody thinks that there's 1,000 Gauss field sitting below the surface. So anything less than that is fair game.
Do you just incorporate the radial, or do you also have to feed it?
No, this particular simple this is a back of the envelope calculation. This is a sanity check, and it's inviscid and just purely radial local Cartesian. Yeah. Okay. But this is just a sanity check to sort of give us an upper bound in a sense, right? So this is essentially a vertical field. But for this field here, this is cool. This field is also nice. It's just nicely hugs. So actually, it's kind of everything's kind of radial, right? It's kind of like it works. But anyhow, this is just again a sanity check.
I mean, you have a colloidal field, you have a shear. You have a toroidal field because you expect the shears.
Yeah, we're being a bit dodgy. So. So we're going to be doing a linear stability calculation around a knot equilibrium. Okay. Now, I know that bothers you. Yeah. It bothered me. Yeah. But
you got over it.
I got over it. So that's a great question. We have time. So. Real life never has linear stability configurations the way we create it on paper, right? Yeah. If you build you know, a house of cards, a stack of cards or something in blocks or something like this, right? Toddlers stomping around the room, and there's always noise and there's stuff, and the house is settling, and so if you wait long enough, it'll eventually fall down one way or the other, right? But you can ask, like, it's all about time scale separation, right? Basically, so if the induction is happening on some sort of linearish time scale, and then you have this instability with a strong growth rate, then you can say that, okay, there's some like unstable physics in the problem that's kind of doing your job, right? So this is the idea. So everything I'm saying is a proxy, and the real goal standard would be to plug it all into a nonlinear calculation, see if it does. But to get our initial conditions and like learn the parameter space that we want to be in and stuff, it's a bit of a night vision goggles, right? So yeah, all of the calculations I'm showing you are by definition wrong. But using some different polynomial fields and others that I'm not showing, you get modes, right? And I don't recall which is what. There's some differential rotation profiles that have been tweaked, polynomial fields that have been tweaked in these things, and you can get different localizations near the equator, different length scales, different depth tendencies, and so on. But it's a mode, right? Who would disagree? And to me, at least, looks quite a lot like qualitatively this is a mode-like structure similar to the torsional solutions, right? And we haven't, and I don't think we want to like fit them perfectly because I'm sure we're missing something. But yeah, so when it came to discussing laws, qualitative laws, there's one that has been produced since the 90s, which is called the helicity law. And people, including Nick Rummel and others who I know, have looked into it with a lot of explanations. But we didn't set out to try to say anything about the helicity law. But there's a law that's observed that the current helicity, the correlation between current and magnetic field, it has this hemispherical law where it's negative in the northern hemisphere and positive in the southern hemisphere, and that's independent of the solar cycle. And lo and behold, without trying, the modes have it. We don't know why, but they do. We checked it. We were looking at the pictures and saying, look, they have a correlation, and there it is. So perhaps that's another clue that these modes, these MRI-like modes, refer to generate. So the helicity law may be kind of a nice bonus that we were never actually thinking about ahead of time. And I will tell you, not all the modes have quite that nice. So this is putting your best foot forward. But in principle, these modes could explain the helicity.
This is helicity perturbations.
Yeah, that's right. But there is no helicity of the background by definition, because the current goes that way and the field goes that way. And then there's no helicity of the background integrated with the. So this is the measurement. That's a mode. Maybe they're the same, right? I don't know. We have a lot more work to do. Quite a lot. And then, yeah, I probably won't get really to the other stuff. We'll see. I slowed down too much, but why not? So then the idea is like, well, this is just the beginning of the solar cycle. So we're writing a paper right now, finishing a paper with a title, something called like evidence that the beginning of the solar cycle begins with magnetorotational instability. So we're certainly a long way away from explaining the whole show. The question is, how do you regenerate this background field from the instability? But this is getting into sort of these essentially nonlinear dynamos, work that was done by a PhD student, Nick Rummel, and others. But like there was this beautiful work by this guy Kelly Klein, which generated instability from the magnetic state, and then the secondary instabilities of that thing was enough to regenerate the background field to begin with, and the whole thing, would have died away had there not been some secondary field. So we're kind of thinking along the same lines that you need to generate eigenmodes that then have some secondary instability, which we don't know yet, that wiggles around in just the right way to do it. And these are magnetograms over about a year or so. But the point is that they sort of sit there, right? They're big, and there's a relative. There's certainly an m equals 0 component to this, but there is n equals 10, 20, 30, I don't know, but it's not n equals 1,000, right? It's not like turbulence, right? It's some modest rise, and perhaps that is enough. And the Babcock Lake mechanism is shown to be enough. So sort of the observational implication of this is actually enough. And then the sunspots are perhaps just pimples. They're just like distraction in the sense. If that's all you can see. You could envision these things coming from down deeper and arriving at the surface. But if you see that, you're like, oh no, it was just there all along, and it just had some problem. And there you get a sunspot. So that's what we're thinking. And then in 5 to 10 minutes, I'll rush through this. This is where I did some. In the meantime, while I was waiting for Daedalus to happen, I was doing some math, and I like to do this for fun, not for profit. The best model of a cat is a cat, or preferably the same cat, right? Norbert Wiener said this, and it's great wisdom. So astrophysicists, I like to think of them as they're like field biologists, right? They're like brave and bold, and they want to go out into the jungle and understand the wild, dangerous accretion disk physics or something like this, right? With all of the dust and all that, or this like angry tiger, and good for them. But you might. Nobody ridicules them, but sometimes people ridicule somebody who thinks they're going to understand something about a wild type jungle cat by studying a house cat skeleton. But I believe you can and you should, right? Like you certainly won't learn everything about it, but you certainly will, and we'll learn about how dinosaurs and how between Tyrannosaurus turned itself around by grading scale models, right? So I did that at some point, and rather than the whole thing, we just do magneto-taylor co-ed. Narrow gap, so everything's going to be Cartesian now. We have a constant shear, which can be either positive or negative. So to simplify the hell out of it, now we have real instabilities that you can do in proper sense. There's some equations, okay? Don't worry about them. But the point is that if you do the right non-dimensional parameters, you find that there's some leading order balances, the velocity, and so on, are all related to this yet unknown function, which I'll call phi. Which I call it order parameter in this matter world. And the point is, if you know that, you know everything else, okay? And you just need to find an equation. You go to the next order, and ta-da, you get this equation that could be cleaned up a bit more, but for now, this is it. There's some parameters in there, but it's this like wave-like equation. You get a wave time derivative. You have a fourth order dispersion term, and then you have a second one. Okay, and then there's some nonlinearity, and it's probably difficult to see here exactly what's going on. So tidy it up. And I derived this equation when I was in Berkeley on a visit, and I went to Edgar the next day, and I've seen that before. And you've been in Edgar's office, and we've probably been in his office, and it's interesting. So he finds some stack, and he goes like, and out comes this paper from 1981 by Jerry Holmes and Philip Marsden, or Jerry Marsden and Philip Holmes, sorry. And they had this differential equation derived as the weakly nonlinear instability of an elastic Euler-Bernoulli beam. And they proved in this like 80-page paper that it was the first example in history of a partial differential equation with chaos, provable chaos. And it's funky. You got a wave term, and you get this big term that would act like a wave speed if you think. And then if this was just a constant speed, this would just be the wave equation. This is a beam equation right here. But then this term here can be positive or negative, because that's your stress or your tension. And then this is some integral. So it's non-local. I mentioned this the other day. I was like, I have an so this is cool. So this Euler-Bernoulli beam, it's kind of like Ginsburg-Landau. It shows up all the time. Well, now I know two cases where this is shown up. And of course, you can simulate it in Daedalus, and it's fun. It looks like a whoa. I'd like to make sound out of this here as well, but it's cool. So you do this, and so this is a Magneto-rotational instability, or a buckling beam. Okay, and then what's cool, so then I this paper about it. You can make analogous the magnetic field and stress, and so there's a story there, and you could create a mechanical analog of the MRI if you were so interested. And again, it's a really simple equation, but it does simple stuff. It's kind of like the chaos equation in some ways, if you know what that is. But, and then you can keep going with the maths and fun. I'll wrap up quickly, but you can. It turns out that because it's nonlinearity is strictly an integral, it doesn't cascade in the way that fluids do. Every single finite Fourier truncation is an exact solution to the equations. Okay, so that's weird. So you can discretize this for any number of exact ODEs and study those. And there's this like, it's just rotational dynamics locally with some nonlinear mean field potential. And every single one of these things has got a conserved angular momentum. And so basically what it is it's a bunch of marbles that are running around a track. Every marble conserves its own angular momentum forever, but all of the marbles together can flex the track outward and in spirit, and then everybody, because of that, drifts outward, and then that puts less stress on the track. The track flexes back inward. Everybody runs into the center and spins up, and this dynamic can happen in a chaotic way, right? So they don't interact with each other, but they just have this mean field interaction. So that was kind of a cool surprise. So I'm actually at the end here. So there's it is. I think the magnetorotational instability is happening in the sun. I believe it is. I don't know for sure, but I think it's something interesting about it. And then you have a buckling Euler-Bernoulli beam. This is a New Zealand after an earthquake, and then it turns out it's also analogous to a bunch of roller derby skaters going around a track and flexing it in its mean field way, and some weak field limit, but of which the sun would obviously not be in. But that's basically where I am. It's the end.